Yes, Doctor, we can hear you.
Okay, okay. So thank you. We're going to start in about 2 minutes. I'm going to share my screen. Just a second. Can anyone just try the feature of raising the hand just to see if it is going to work on my other screen? Yes, it does work. Thank you very much. Thank you. Yeah, so during the presentation, if you do need to ask a question, just raise your hand. I cannot see like most of my screen, but raising hand, I can see it, okay? So during the presentation, if you have any questions, so just let me know by raising your hand. I'm going to try to share the presentation. You should now be able to see the presentation. Okay. Okay. Does anyone have a question? Like I see like some hands raised. Is there any specific question?
Yes, Doctor, can we speak today about project
About what? Sorry?
about the project?
Yes, we'll talk about the project. Yes.
Okay.
Okay. Just a second here. Okay. Okay. So we're going to start. So welcome to the first lecture on reinforcement learning. I see that this is already being recorded. So just be aware that this is going to be recorded and it's going to be available only for the students registered in this class. Okay. So my name is Sidney GVG. I'm a professor at the School of Computing at Queen's University. I I work with robotics, autonomous systems, a lot of control, and we do use machine learning for all of that. So the idea is to use these types of systems in order to develop solutions that are going to be ported to real systems. My experience in reinforcement learning is almost 20 years already. I have been developing this for vehicles, for self-driving vehicles, for mobile robots, for drones. Um, and I lead a lab here at Queen's. It's called Quarg, and we do have like 3 postdocs, around 11 PhD students, and 4 master's students. So this is and all of them they work like in areas that are similar to the ones that we are going to talk about in this course. I'm going to use lots of examples of things that we have been doing. So if you have any questions, don't feel shy, just ask me the questions. For this course, we are going to have 3 assignments, and the division in terms of like a weight for the assignments is as you see on the screen. The first assignment is going to be 10%. I'm going to release like, and you probably have seen that it's I think it's going to be released like after the lecture today. It's already automated, so everything is going to be released automated. The first assignment is going to be due in about 2 weeks, I think. And then second, third, you can look at the syllabus for the details on the dates. And then we're going to have a project. This project is going to be 60%. I know that we have an odd number of students. So we have 49 students. What we're going to do, we're going to have 12 groups in total. So it's going to be like 11 groups of 4 people and one group of 5 people. Okay. So I will allow you to sort out like which group is going to be like 5 people. But the group that has 5 people, um, in the proposal, we are going to have like a proposal submission at some time after you get more familiar with reinforcement learning. In that, you have to be very specific to say what you are going to be doing that is going to require a fifth person. Okay, so I expect that the amount of work for the 5 people group is going to be a little bit higher or than the one for students. Okay, so you should try to um, calculate the amount of time that you're going to use. For example, a good amount of time in projects that we use in grad courses is about 40 hours per student. So the project has to be commensurate to that. So if you have like 4 people, so that's going to be 160 hours. If you have 5 people, it's going to be 200 hours. Okay, divided among everyone, and this includes the programming of the project, the design of the project, and also the writing of the project. Okay, so in the project, you're going to submit your solution, that is your code, and you're also going to submit a report, right? So the format of the report is going to be released later on, so that you know what you need to provide, but it's similar to a paper. So if you're familiar with papers um, in IEEE. So it's going to be kind of like that format, like a double column type of format. And it flows the same way, right? So have an introduction, problem formulation, then what is your methodology, what your results were, and a conclusion. So that's basically the format. Okay. Yes. So there's a question.
Yes, Doctor. There is 13 available group in on queue. Can you edit this and make them 12 and one of 12 group would be 5 members?
Yeah, so if you send me the 5 names, and then 4 of you can register in one group, and then you just give me the fifth name, and then I will enter the fifth name manually. Okay, so it can be done that way. So, for example, if your group is group number 2, let's say, so 4 people will register, and then you send me your name, and then say, "Oh, I want to be registered in group number 2," and then I will add the fifth member. Okay.
Okay.
Okay. So, any questions on the course evaluation so far? No? Okay. Um, you are already familiar with the policies at Queen's for the use of Gen AI and other things. In this course, you are allowed to use Gen AI, but you have to explicitly state what you did. Okay. So, for example, you have to tell me what model you used. You have to tell me what are the prompts that you used. If you used automated generation of code, you have to tell me exactly what you did, and please give me like the steps that you followed. Okay. And again, this is something that is normal in other situations as well. You should, because be aware that like in all of these systems, they are going to use some um, formats and codes that are actually from other repositories. It happens, and you do need to check for that. Okay, So because you cannot just use repositories, even if they are acquired by GenAI, you're not allowed to do that. So that actually is plagiarism according to the policies. But you are allowed to use it, but you have to be very specific, very explicit. For the assignments, my recommendation is that you don't try to use it, because if the assignments are built in a way that it's for you to get familiar with the ideas, and you cannot develop the ideas unless you actually try that by yourself. Okay, so you're going to be, it's going to be counterproductive for you. Take this opportunity for you to learn the basics and then what is the ideas behind it. Because otherwise, even if you like later on you try to do a project, if you don't understand the basics, you're going to actually go on doing things that you should not be doing, and it's going to just waste your time. Okay, so for the assignments, I encourage you to do that by yourself, just to make sure that you understand the concepts. Um, Specifically for the project, I know that it's unavoidable nowadays to use these types of solutions, but you have to be very specific on what you did. Okay, so when you submit your project, I will ask you to submit, for example, I'm not an appendix with like what was your use of GenAI. Okay, but again, we can talk about this later on as the course progresses. There is a TA at Queen's for this course. He happens to be my PhD student, very knowledgeable on reinforcement learning. He has been working on that like for a while now. So he will have some office hours as well, specifically for the assignments. If you have any questions, so then you can go and then you can ask him. Okay. This is going to be announced later. It depends on what is the availability of the students as well. I do not know now exactly what is your um, uh, availability. He is going to post a survey on OnQ to decide on a time for you to meet. These sessions are going to also be recorded. So if you cannot make to one of these sessions, you can watch the sessions later. Okay. But again, we will discuss that in more detail as time goes by. Okay. Any questions? So this is like like just introduction of the administrative portion of the course. And now we're going to start with the technical portion. Okay. You probably have seen this definition before. So it's a definition of what machine learning is. And in this case, we are talking about machine learning to solve specific problems. And these problems can be like whatever you want to do, right? So it can be a classification problem. It can be a regression problem. It can be a control problem, like in reinforcement learning. It can be a natural language processing problem, machine vision, whatever. So it's the same idea. So here we have these systems that are trying to learn from experience for a certain class of tasks. So these tasks that we are going to be learning from, they are tasks that are defined beforehand. So you have this class of tasks that we are going to try to solve. And we have some performance measure that is going to be linked to this particular task. And this performance varies from like certain uh, tasks to other tasks. For example, if you're doing classification, so the performance is like how accurate this classification is. If we are doing like regression, is how closely we can approximate like a function of some sort. If you're talking about like a natural language processing, so we are talking about like how this natural language processing can be done in and then how good it is, right? So in the same way that when you're going to do distillation of LLMs, so that's that performance. Um, but the objective is that this performance is going to improve with experience. So that's the general idea. And there are different ways that you can see this. Like later on, if you want to go on this link, you're going to see, like, for example, learning digits. If you have like a whatever like data set like MNIST or whatever other one that you want to use, you have like samples and you have samples that have never been shown. And in this particular case, you try to guess or to identify what these digits are. So that's one way of doing this. You can think of that as like recognizing um, like the type of pictures or figures. Like for example, if it is a cat, it is a dog. So that thing, right? Or we can do this if we want to predict like a variable. Like for example, you want to predict if a given engine is going to fail. So then you have data of normal engines and then engines that are about to fail, and then you identify or predict when that failure is going to happen. In all these tasks, what is implicit is that we do have a task that we know what the output is, right? So, for example, if we're doing identification, we know what the output is. Or if we're doing even like natural language processing, we know what a normal interaction is going to be. In reinforcement learning, this is going to be a little bit different because we do not know what the solution is. We have like this measure, this performance measure, but we don't know if something is successful or not. And then we have to have a secondary measure that is going to give us that measure of success. So that's the difference that we have in these systems here. But again, we are going to go into more detail later on. So this is just to introduce what the problem is. And this is just a block diagram of that, right? So you have experience, and the experience is going to impact the task. And then in reinforcement learning, this is going to be a little bit more um, uh, intricate than in other systems, but it's present in everything, right? So then by that, we have a measurement of the performance and the experience through the selection of certain parameters is going to improve what the performance is. So that's the general idea of how we are going to be doing this, okay? And again, in machine learning, so the difference is that in traditional programming, we have an input, we have a task that we want to do, and then we get the output. In machine learning, we have the input and the output, and then we get what this relationship is. So we try to find what this map is going to be. In reinforcement learning, this map has a very specific format, and that's one thing that we are going to see throughout this course, like how we are going to be doing this. For these systems that we are talking about, we generate actions. So we have some inputs. These inputs can be called different ways, but they are percepts, right? So they are usually like things that you observe from the environment. So sometimes we call this percepts, sometimes we call this observations, sometimes we call this states. Okay, but they refer to three different, slightly different things, as we are going to clarify during this course. But this is something that allows us to perceive what the environment is. So it can be like sensors. So that's why it's this generic name. So you can have, like if you're talking about a robot, it can be a camera. It can be like physical sensors that are going to measure what the state of the environment is. Or if you're talking about like software agents, it can be like data, right, that comes from a database, or it can be like an observation of a state of something. Like for example, a network. So it's very popular nowadays to use reinforcement learning for cybersecurity, for example. And then what you do, you have like these percepts that are going to be linked to observations in what the network is doing. So this can be like the traffic of the network. It can be the types of processes that you have in the network, or the nodes, how they connect or disconnect from the network, these types of things, okay? Then we have layers of responsibility. We go from very low, that's what we call like reflex systems. So systems that will have perception, will have actions right away. And you can think of that, for example, if you drive in your car. When you drive in your car and you see something, like someone brakes in front of you, so you just brake, right? So that's a reflex system. So you see something happening and you brake. That does not take any deliberation in your brain, right? So you just react to what is happening. Um, and this is the first level. This is extremely important because without this, you cannot get like actions that are going to be stable in the long run. Then you keep going up in these levels of abstraction, all the way to this knowledge-based deliberation. And again, here, knowledge-based deliberation, it does not mean that you have to have like a knowledge-based type of database as people used to do, like up to 2000 or so. This can be represented as a system that is a high-level abstraction system, similar to nowadays like an LLM, right? Or an agentic AI type of system that is going to be located in this high level there. Okay, but the type of information that you need to have is different. For example, like in your car, if you're driving your car, if you're just driving around and you have no objective, so then technically the only thing that you need is a reflex system, right? But if you have an objective, if you want to go somewhere, so you want to go from home to work, and then you have like different paths that you can take. Now you have a deliberation that takes into consideration the knowledge of your city, right? So what are the roads? And if you know if a road is going to be blocked for some reason, so you try to avoid it. If you know that there's a traffic jam, so then you're going to try to avoid it. If like in some cities, there are areas that you don't want to go because like the roads are bad, or it's dangerous for some reason. So then that goes into this knowledge-based deliberation. Observe that this is not a reflex system, right? You have to have more information in order for you to actually act on that. And you have to make some interpretation of the percepts to bring that up to that level of abstraction. And again, we are going to see some examples today, but throughout the course, we're going to see some other examples. Okay. As I mentioned before, since my experience is mostly with physical systems like robots, most of my examples are going to be on that, but we are going to have lots of examples on other systems, like, for example, games and other types of interactions. And that's going to be a little bit different. But most of the things that I'm going to talk about, they're going to be linked to physical systems. Okay. So this, and if you go to the literature on this, this is extremely large and extremely old, right? So, and we are talking about like these types of agents that were firstly designed, I don't know, like in the 70s, maybe, so over 50 years ago. But the ideas, they have evolved, but the components, they are kind of the same, okay? So usually you have an environment, and then you observe this environment through sensors. And again, here I'm using sensors in this broad meaning. So it's not necessarily just a physical sensor. It does not need to be a camera, for example, or a microphone of some sort. It can be something that you observe, like, for example, the state of a board in a game. So it can be something like that. Then from that, what you have a representation of what the world is like right now. To that, we give the name states. So that's going to be the state of the environment. Observe that the state is a representation of the environment. So the state is not the environment, but it's a way that you interpret the data that comes from the sensors. Then, in the most simple way, and then this is something that, even with animals and people, this has been shown that we behave like that, and then animals in general behave like that. We have a certain condition action rules that we execute if something of a certain input happens. Okay. So for example, if you touch something that is that is hot, you're going to have a pain signal, and your brain and your muscles, they are going to react right away, right? So that information, most of the time, is not even processed like by the high functionality of your brain. So it's going to be like just this immediate system that something happens and then you act on that. If there is a dysfunction on that, for example, if this signal is not processed properly, so then you don't have that pain signal, and then you can actually get hurt, right? And there are some dysfunctions that happen with people that you don't have that. Either like the transmission of the signal is cut off, or sometimes it's just that your system, like your brain system, like your neurological system, does not respond properly. Okay, but this is something that is very, very fast, and it's not necessarily very structured. So, for example, you touch something that is hot, your muscles are going to contract, and then you're going to move away from the source of the pain. Okay, in like robotics, for example, there is a system that is very similar to this. And here is the demonstration of a system that does what is called a random walk. So you have a robot that just goes around, and this robot goes up to a certain obstacle. And then when it finds that obstacle, it turns, but it turns it at a random uh, like angle. And this is what we call a random walk, right? And this random walk is also used like to represent other things like physical systems, right? Like noise in systems and things like that. This works. And this is like if you have seen like these robots that clean houses, like Roomba and something similar, like the first ones, they worked exactly like this. There was nothing planned on that. They would just go around, and then if it hit something, it would turn, but not turn like a specific angle, but just a random angle. You can demonstrate that if you want to cover an area, this is going to cover the whole area with probability 1. However, you need to allow for a long time for that to happen. And this may not be very efficient. And again, the reason is because we are just looking at the reflex. We are not looking at the planning. And in reinforcement learning, we are going to try to put all of these things together. We are going to try to put like the reflex and the planning together. So that's the idea. However, in the literature, so people came up with other ways for us to do that. One way is to put a model in these reflex agents. So now the agent has a representation of how this world evolves. So that's what a model is, right? So it's the same way like when you were at high school, for example, and then you're learning how like something moves, like according to like Newton laws, for example. So you have a state that is like a bunch of numbers that represent, like, for example, positions of things. And then you have the relationship of how that is going to evolve. So you apply a force, you know the mass of the system, and then you can find what the acceleration is. Or if you have the acceleration and the mass, you can find what the force is. So that's the model, right? And whatever your action is going to be, if it is going to be the force, for example, you can predict what your system is going to do. And then you can represent that at different levels of representation, right? So you can have a dynamic system that is going to be linked like to the forces that are applied to the system. You can have like a kinematic system, like for example, that you have the velocities and the accelerations, but you don't necessarily have like a representation of the mass and then how the forces are going to interact. So it depends on the problem that you're trying to solve. But now you have a model of the system. Since you have a model and since you know what your actions are going to do, you have a better way to find what you should be doing. Okay. And this exactly happened like when people implement like the more sophisticated Roomba robots or these vacuum cleaning robots in this the first system. So you didn't have to have a model of the whole environment, but what you could have is just a model of what the system is going to be doing. And again, This is already like maybe like 10 years ago. So what these systems would do, they would get close to a wall, and then when they sense something, they would turn exactly like to the side, walk a little bit, and then 180 degrees, and then keep going on this what we call the lawn mowing pattern, right? So like going like across the whole environment. This is clearly more efficient than using a system that is just random. So that's the idea here. And there are different models that you can use. Like the most modern systems, they have way more sophisticated ways. Like for example, they have a representation of the environment that is based on a map. So the state is represented as a map of the environment. So basically, you put your robot there, it runs for a while, and it identifies the map of your house, and now it can optimize what is the best path for it actually to clean the whole house. And it knows, oh, here there's a sofa, and then I cannot go under the sofa. So I know that that area there is not going to be able to be covered. And then you get like a better pattern to go around it. Okay. So that's a better model. But this is just to show you there are different levels of models, right? So models, they can have very simple meaning or a more complex meaning. And then you can use that to make your solution more efficient in the sense that you're going to spend less time, less energy, people are going to be happier, and things like that. Okay, so that's the second level, right? So we had like the reflex agent and the model-based reflex agent. However, observe that here we don't have this concept of a goal, right? The goal is not there yet. And technically, the Roomba has a goal. The goal is to clean the whole area. And then you have to have a metric of how you actually do that. This brings us to a different type of agent that is called a goal-based agent. Now, instead of having like the rules of what you're going to be doing, like the old Roomba that you would only go and then turn like to the side, move a little bit, and then do the lawn mowing type of thing. Now, since you want to clean the whole area, you have to have a goal and a metric to decide if you did that. So now it's kind of the same idea, but now you have a little bit more reasoning in your system. So observe that now we are going to go into the more abstract type of thing. So if you have an objective, so you have to represent that, and you have to represent how satisfied you're going to be in that. And one example of this, like in robotics, for example, is how I get to a goal, like in this case is a position, but you can think of that as a more abstract goal, as like cleaning the whole area. And then you have an obstacle. The obstacle is something that you want to avoid. So then you have an attraction force, in this case, to the goal, and a repelling force from the obstacle. And then you have a resultant that you can execute on the robot. So the robot goes towards that goal. One system that uses that, like in robotics, is like the rovers that are sent like not just to Mars, but to other places, because the systems, they cannot be teleoperated. They are so far that whatever command that you send is going to take minutes to get there, even if it is just on the moon. So it's going to take seconds to get there. And this is something that you sometimes you cannot do because it's going to risk your vehicle, your system. So in this case, you have like an objective, for example, in Mars. Oh, I want you to go to this position. But since you don't see everything, and the environment can change because you have wind, you can have other things, you go there and then you look at what is around. And for example, if the robot needs to go to a point, but there is a big rock in front of it, or there is a hole that you didn't see in the beginning, so then the robot is going to react to that by represent these types of systems in this way. Okay, so that's another way for us to see the same objective or the same task. Okay, but it's now you have um, more examples. Then we can The issue with that is that the goals, they need to be of a certain type. Like, for example, if you look at that, this robot here, so the robot is just looking at covering like an area or to go to a certain point. So everything that you're measuring is the same thing, right? So it's like distance, time, or something like that. What if you mix that? Then you have to transform all of these to the same function or the same loss or reward function, like in the lingo that we are going to use. And this is going to represent how happy you are to be in a state. And this is a utility that you represent. And this idea comes from economics, right? So it's like the idea of like if you're going to a grocery store and you're going to pay something like for, I don't know, a banana and an apple, and the prices are going to be different. So how do you actually measure that, right? So it's because there are different things, and these different things, they are some of them they are untangible, right? So they are linked to how hard it is to produce that, how people like that particular fruit, how people value like the energy content of the fruit, and so on and so forth. But these are very difficult for you to do because it's very difficult for you to set how more worth something is. In economics, we do all of this and we create a single signal that is the price. And the price is going to tell us like how worthwhile it is for you to have something like that, right? And again, this can be manipulated. Don't get me wrong. I'm not saying that this is perfect because someone can actually try to sell you something that is completely worthless. But if you perceive that as being worthwhile, so then it can backfire. Okay. But the idea here is that you have a utility, and this utility is going to encode how happy you are to be in in a state. And we are going to make use of this in reinforcement learning quite a lot. So that's one of the central ideas of reinforcement learning, that we can transform how good it is for us to be in a state to a single number. This is extremely powerful. Okay, so we are going to come back to this later on. Observe that in this case here, up to this point, we are not talking about like learning or anything. We are talking about like representation of the problem. But it's this representation based on utilities is so much more powerful than the previous ones that we can use this. Okay. And again, this is not something that is just in reinforcement learning or in machine learning at all. There are lots of other systems. And again, if you have taken courses like in control systems, so that's what you do, like these loss functions or utility functions for optimal control. So that's something that you are probably familiar with. In communications, so there are the same idea, like how you actually value things, like in terms of bandwidth, in terms of the speed of the connection, and so on and so forth. Okay. One simple way of doing this, or of looking into that, is the problem, for example, when you use a GPS, when you use your Google Maps, like to decide how to go from one place to the next. And you can have like a different values there. And this, you can set it up, right? So depending on your own habits, you probably have seen that like Google Maps, you can actually have like these green leaf type of paths that are going to be like more fuel uh, uh, economic, and then you can use that. Observe that that does not mean that you yourself is going to necessarily save money, right? So that's like what is perceived to be good for the environment, which is that you're not going to consume a lot of fuel, and then you're not going to have a lot of CO2 emissions. But if this makes you drive like 30% more, you're going to spend like more tires, right? More oil, more other things. And in the end, at the end of the day, it may be actually more costly for you. But this is implicit the idea that you value not having this impact in the environment in terms of CO2 emissions more than other things. Okay, so that comes from this utility. But you can actually say, okay, no, I just want to get somewhere fast. So this means that in your utility, you value getting places faster. And then you say, well, I want a balance between the two. And that's a different utility. Okay, so there are lots of different things that you can put in there. You can actually say, okay, I want to avoid toll roads, right? Because I don't want to pay the toll. And that's another utility, and so on and so forth. So it depends how you're going to actually set it up. My point here is that you can have different utilities. And these different utilities, they are going to drive what the best solution is going to be. And with different utilities, you're going to get different solutions. Keep that in mind. That's extremely important when we go forward with reinforcement learning. So now we get like to this learning-based type of agent. And here is much closer to what a reinforcement learning agent does. So now we do need to have a performance standard in terms of what is going to be the utility that we are going to be using. This, in the language of reinforcement learning and for other control problems as well, we call that a critic. A critic is going to try to evaluate how good it is for me to be in a given state. Okay? This is going to tell us how we should react if we have an action that takes us to a given state. Then we have this learning element that is going to be our um, uh, the way that we are going to set up the adaptation in our system. This is going to be linked to a performance element, and this performance element is going to be linked to how good we see our environment and what the objectives of our environment are. We're going to see that in reinforcement learning, we mix like these things in a very particular way to make this system to be more effective. Okay. In the end, what we want to have some actuations, some actions that are going to change the way that the environment is going to respond. Observe that here we get an input through the sensors, and in all cases, by the way, and then we generate an action through the actuators, and we change the environment. But there may be much more things that are going to change the environment. We are not the only thing that is changing the environment. So there may be some other elements in the environment that we don't control. So we only control portion of it, right? Not the whole thing. And then you are very familiar with this because you live in the world, and then you know that you cannot control everything that you have in the world. So for example, and this is an example that is used quite a bit in reinforcement learning, this is driving. And this is an environment that actually exists. It's a little bit old nowadays, but it's still like used a lot. Here we have racing cars. And these cars, they are in a certain environment, and they go and they try to get into these um, uh, the representation of what the environment is. And this comes back to the idea of how we are going to value the utilities. And it is quite clear, like if you look like different styles of driving, right? So if you look at, if you watch like Formula One, for example, you have like a different drivers that are going to race differently because they have like a different things that they value and different things that they are good at. Also, the cars are different, and then you have to adapt to these different things. Okay. For a car like this, like the first approximation is how fast you can go around the circuit, right? So let's say how fast you can do a qualifying lap, right? So if you're just driving by yourself, how fast can you do that? So that's the first approximation. In that case, your utility is just how fast you can actually drive. Okay. This does not mean that you should be driving at the maximum all the time. You will be driving at the maximum that the circuit allows. Like, for example, if we are going to get close to a curve, you do need to take the curve. Therefore, you do need, in lots of situations, you do need to take the curve. But in lots of situations, you do not need to take the curve. Therefore, you do need, in lots of situations, you do need to take the curve. Therefore, you do need, in lots of situations, you do need to take the curve. Therefore, you do need, in lots of situations, you do need to take the curve. Therefore, you do need to slow down, right? So you can actually take the curve. You will change the way that you're going to drive, right, within the circuit to take that curve. All of these is going to be implicit in what you're going to be doing. Okay, that's a first approach. But let's assume that now you're going to race against other cars. That's different because now, if you're racing, you have other cars ahead of you, behind you, besides you, right? So that you need to react differently. If you have a car in front of you, you want to pass this car and you want to avoid hitting this car. So it depends on how much risk you're going to be allowed to take, right? If you're developing a reinforcement learning system for this, you are allowed to take a lot more risks, right? Racing car drivers, they have to take risks if they want to win a race. If you're doing this for a self-driving car, is completely different. You don't want to take any risks. So you don't want to get into an accident. Getting into an accident is really, really bad for you. For a racing car driver, so like getting into an accident is a risk that you, in some situations, you're allowed to take. But you want to avoid, like as much as possible, right, to hit other cars. If there is a car that is trying to pass you, so you're going to change the way you drive. Observe that these are different utilities or different portions of a utility function that you have to take into consideration. And depending on what you want to do, like for example, have an agent that is really good at qualifying. So then you can develop that. If you want an agent that is really good at racing, you can develop that, and so on and so forth, right? So you can have like an agent that is very defensive, and this may be good. I'm not sure. So, but you get like what I'm trying to say, right? That you can play with this, and this is exactly what reinforcement learning, where reinforcement learning shines, right? Because this is like something that we want to do with reinforcement learning quite a bit. In the context of these ideas, like putting all of these together, we have this particular scenario. We are going to talk about like each one of these components in detail later on, like today. After we are going to have a break, like a kind of like a 10-minute break when we get to the end of these slides here. And then we're going to talk about each one of these components separately. But just so we can start like exploring this in the context that we are looking at, we can have a simplified diagram. We have an environment that is where our agent lives, and our agent can change this environment. How the agent changes this environment? It looks at the states, and this is by through the measurements. And then based on that, it chooses an action. The problem here is that the action is not a prescribed action. If we knew in this state, we should take this action, like for example, if you operate something like in a factory, maybe some of you have already worked in factories. I worked in factories before. And then you have like, okay, if this is the state, that's what you need to do. So you're trained to do that. Okay. But that's already given to you. In lots of situations, this is not given to you. You have to find out what is the best way to do something. And this is like what the agent does. You observe the state and then you choose an action. How do you know how good your action is? You look at a reward that comes from the environment. So it's something that like in this case, if your agent is a dog, so the reward is going to be a biscuit of some sort, right? And then you have to react to that. Within the reinforcement learning problem, there is another issue that is when we do an action now, the reward may be delayed in time. And this happens because the environment can be complex. And then the task that you're trying to solve may be complex. And then you have to put all of this in the same package. We are going to see that in reinforcement learning, there are lots of ways for us to solve for this problem. Okay. But because we are not looking at just what is the reward that we're going to get now, but we are looking at the reward that we're going to get in the future as well. Okay. Yes, there's a question. Please go
Uh,
ahead.
yes, doctor. Is the reward is a number fixed number, or does it change and become graded depending on the problem?
So the reward, we're going to see this very soon, but the reward is a number. It's a quantity, right? It's a scalar. It's a real number most of the time. Um, the format of the reward can change. Like for example, there may be some tasks that you do that they are very beneficial to you, and then you have a reward that is a very large number, or something that are very detrimental to what you're doing, and this reward is a very low number. So all of these can actually play a role. We're going to see examples of that later, but usually, most of the time, the reward is a number, and this is a number that can be scaled, but it can be like in the general case, if something is bad, it is going to be a negative number. If it is something is good, it's going to be a positive number, but you can scale
So,
that differently.
okay, so we can change the reward number. It's not fixed, based on the reward that we can put it. And so it's hyperparameter, not parameter for the model, right?
So the reward is given, it's an interpretation of how good the environment is. Once you define the reward for your problem, the reward usually does not change. What I'm saying is that you can value the reward differently. And if the reward changes, so then you have a different learning system, right? So there are different approaches to that. For example, ensemble learning of some sort and things like that. But in the problem, usually when the reward is set up, then the reward does not change over time, like in terms of the format of the reward. Because if it does, so now you have another problem that you're tracking a function that is changing over time. So we're going to get there like into these details, right? So right now, just think of that the reward is a scalar number. And this scalar is going to be given to you based on an interpretation of how good the environment looks to you right now. Okay, so
So,
that's
okay. So if the agent have the problem or make mistake, big mistake, it's the same that we have the agent make a small mistake, right? Because the
no,
reward and
not necessarily, not necessarily. What I'm saying is that the reward scheme is like a yeah. I think we are not talking about the same thing. The reward scheme is going to give you numbers that are for something that is good or bad. Okay.
okay,
There are things definitely that are way worse than others. So for example, in the case that we are discussing here, if you hit another car, that may be very bad. And then you can give you, like, for example, um, a reward of minus 100. If a car
yeah,
passes you, this may be bad, but it's not going to be as bad as you hit something. Okay. So then your reward is not going to be the same, minus 100. It might be like, I don't know, minus two, right? Because you can still win, right? But once you hit something, you're out of the race, right? So these
right.
numbers can be different. What I'm trying to say is that once you define that if you hit something, your reward is minus 100, and then you say, oh, but now my reward is going to be minus five if I hit something. So then you create instability in the system. And that's not the way that this is done. Okay.
Okay, okay,
Yeah,
thank
but
you.
the reward can be different depending on what you accomplish.
Okay,
It can be, positive, negative, and so on and so
but
forth.
for the one problem, there is one reward or grading system, right?
Sorry, for one problem?
For the same problem, there is one grading system or one reward function, one
Usually,
reward
yes.
way. Okay.
Yes, usually yes. And then it can be a number, it can be a function, it can be other
So
things as
we
well,
can't
but it
we
usually
can't
is the
change
same.
this.
It's the same.
We can't
You
we can't
don't,
change.
you usually don't change it. I'm not saying, can you change it? You can. But then this is going to create a lot of other issues, okay? That you have to be aware of. If you're changing that, you're creating instability in your learning because now the values are going to change. And these values that are going to change, they're going to be spread out throughout your whole system. So
Okay.
there are cases that you can do that. They're rare. They're not very common. That's why I'm trying to say that it's not impossible to do that. But in general, once you have a reward scheme, you stay with that reward scheme. Okay.
Okay. Okay. I mean that we can make the reward function more smart or more intelligent, depend on the situation we have or the environment we have, because agent maybe face a lot of environments or a
Yeah,
lot
you
of
could do
problems.
that, but it's this approach is usually called reward shaping. So you shape the reward to the problem that you have. That's definitely something that you can do. But most of the time, once you find the shape of your reward, you it's based on like your understanding of the problem. You don't try to keep changing that afterwards. Okay. But yes, so if you want to solve a problem in a given way, you actually can add this knowledge there. We are going to see very soon that this may not be the best way for us to do this. And the reason why this may not be the best way for us to do that is that if you create a reward function that is really complicated, you're already telling the system how you want to solve the problem. And the way that you want the system to solve the problem is not necessarily the best way for the system to solve the problem, because this goes into your misconceptions of how you
Mm.
would solve the problem. And
Okay.
sometimes you want a system that solves the problem better than you can solve the problem by yourself. Okay.
Okay. Thank you.
Yeah, we are going to get that like when we talk about like a more sophisticated things, like for example, games like chess games, Go games, and so on and so forth. That it's when people implemented systems for that, you usually don't say how you're going to solve the problem. You just try to represent what problem you need to solve. Okay, so but we are going to get there. Okay,
Okay.
okay, okay. So these components, they always need to be identified. Like what are the actions? What are the states? What is the reward? So these components, they need to be defined. Actions are usually given by the problem because you don't have the flexibility to change actions most of the time. Like, think of like a playing a game of chess. You cannot say, well, I'm going to create my own rules of how to play chess. Like now my king, instead of like moving just one square, is going to be able to move uh, three squares, right? Per per play, right? So now you change the game. So you don't have this flexibility to change the actions. Okay. The state is something that is a little bit more sophisticated, like in terms of like an abstraction, because for the same problem, there are different ways that you can represent the states. Okay. And again, this goes into the what you want to represent as your model. The reward is where you have the most flexibility. You can define rewards in different ways, and then you can actually create like a good approximations for these rewards. I'm going to show you an example. And again, the objective here for now is not for you to understand how this problem is solved. And it's just to understand how you model the system, right? It's not even necessary for you to understand the model of the system right now. It is just to understand how this is actually done. What are the components that need to be defined? Okay. So in this problem here, we have a set of UAVs, drones, and then these drones, they need to keep surveillance on a target. This target in this case is this car there, right? The systems, they have like some machine vision implemented, and then they go and they look at the car. The objective is for you to have more than one system because now you have different cameras. And if you have like different perspectives, you can reconstruct what your target is. If you only have one camera, you have a monocular system, you get an issue because it's very difficult for you to rebuild the surface of the system. Okay, even though it's possible when you're moving, but it's a little bit more complicated. If you have more systems, now you can actually get like way better representations of textures, of details of the system. So here, this is the application. So you have like the systems that go around. You have different drones. You have one drone, let's assume, that is really good at tracking. So this drone is going to track the system on the ground. The other ones, they don't have the same algorithm for tracking. So what they do, they look at the target from their cameras, and they can perceive the states of the other drones. So they know the positions of the other drones, right? And then you can represent what these systems are going to be able to do based on that. Therefore, the problem here becomes a leader-follower problem. So you have one drone that is the one that is tracking and then is looking at the ground, and you have the follower drones that know what are their relative positions to the leader. Okay. And you can, since these are drones, you can think of them like driving at or flying at different altitudes, which is actually very common, right? So you don't want them to fly on the same plane. You want them to fly at different altitudes because now you can actually have cameras that are going to be at different locations as well. So that's the problem. That's the setup of the problem. So you want to learn how the followers, they follow the leader. That's it. Okay. So what the way that we want to model this is the states, the actions, and the rewards. So these are the three components that we are going to design. For the follower, we can actually get a representation that is going to be the relative position between the leader and the follower in this fashion here, right? So we use trigonometric functions to represent that. Again, I don't want to dwell on exactly how these equations they work. I'm just saying that we can actually do that. We can represent the relative position of followers and leader, like in this fashion. So then we have the relative x position, the relative y position, the relative heading position. So these are the relative positions there. We can also add in our state space what is the role, like banking, of the follower, what is the role of the leader, and then you also can see what is the action of the leader. So, and this we can all see from the environment, okay? And then these equations, equation 2 and 3, is like you have 6 numbers, is how the 6 numbers are defined. Again, it's not important how they are defined right now, just the fact that they are represented this way. Then we can look at how big this is, okay? If we represent these quantities in continuous numbers, we have whatever like the number we are going to have, we have an infinite number of states, okay? Because real numbers, they are infinite, and then we have 6 real numbers, and then the number of combinations is going to be infinite. If we discretize this environment, let's say that x and y positions are going to be like on a square of minus 150 to plus 150, we have like a certain number of positions there. If we say that the precision that we need is 5 meters or 5 units, whatever these units are, so then we are going to get from 5 to 5, right? And then we go from minus 150, minus 145, minus 140, all the way to 150, okay? For the angles, for the relative angles, we can also create this as well. And then it's, in this case, is every 15 degrees. And then we go 0, 15, 30, up to 345, and then 360 is 0 again, okay? And for the command, that is the banking, so we are going to get like 0, plus or minus 15 degrees, depending if it is one side or the other, and plus or minus 30 degrees. These are selections that I did, okay? I select these. You could have select different numbers. You could actually say, oh, well, in my case, I want every degree. So I want 0, 1, 2, 3. And then instead of having like less numbers, you have more numbers, regardless. So we have this. And I'm not saying that you would need to discretize it. I'm just giving you an example here, okay? But it's if you discretize, this can be made like efficient. That's what I'm saying here. So now, if we discretize, if we have this, right, that we have like x squared plus psi here, uh, like a times psi, like a times like the command 3. So we have a certain number of states that we can represent. In this case here, if you calculate number of states, is about like 12 million states. Okay. And 12 million states is a large number of states, but it's not a gigantic number of states. Like when we did this, we did this like back in 2016, I think. This was kind of like very difficult to represent. Now it's way easier, okay? But the ideas are exactly the same. So in lots of cases, you want to reduce the system because if you reduce the system, you reduce the number of parameters that you have to learn. And if you reduce the number of parameters that you have to learn, you reduce how much data you need to have. And for these types of systems, this sometimes is very useful, right? Because you don't want your system to be running forever. And sometimes, in lots of situations, specifically if you're learning this on physical systems, the amount of data that you need is actually relatively, it's very costly for you to acquire. Therefore, you do need to learn with less data. So that's for the state space. So this is the state space, in this case, like let's say 12 million states, and that's how we do it. The commands, that's the action space. So in this particular airplane, so we have this banking, and the banking goes from these values there. And again, these values, they are common in the literature. It's for a fixed wing is the way that they were using it. And in our case, we can simplify that because we don't want to go from 0 to 30 directly, because that's a little bit too aggressive for the platform that we were considering. So we only bank 15 to 15 degrees. So we only allow that. Then we have, that's why we have only 3 commands, even though we have like 5 different values. So we only have 3 possibilities. Like if we are, R is 0, so we are flying flat, we are flying straight. We can only go to plus 15 or minus 15. We can either bank to the right, bank to the left. That's it, okay? So that's how we represent these actions. Observe that the command here is a coordinated turn, and the only thing that is important for us is going to be the roll command. And this is physical, right? This comes from the system that we are representing. If you're representing a different vehicle here, let's say a quadcopter, or if you're representing um, um, a helicopter, so that would be different, okay? So that's physical from this. So this is the representation of the action space. So these are the actions that we have. Then we have how this system works. And this is usually represented as a probability function. It's a stochastic function. And this takes into consideration the noise that you have in the system. So for vehicles, so this depends, like for drones, this depends on the wind. So if there is wind, if you execute the same command, but the wind is prevalent from one direction or the other direction, the actual execution is going to be different. Okay. In this case here, we are representing this as a kinematic model. And this is just like for simulation purposes, but the system will have something like this. And what is this actually measuring? It is telling you that if you execute, for example, the first action here, so let me just, so you are in this position here and you bank left. What happens is that you can land in whatever positions are like this, okay? Because there is some interaction with the environment that you cannot model. And this is what is going to happen. If you decide to bank left again, the cloud of points grows, right? And then you see that the uncertainty in the future keeps growing. And again, this is very, very similar to what actually happens in real life. You can predict something really well 1 step ahead. But if you have more than 1 step ahead, you get like a way more uncertainty. And this function here represents this uncertainty. In reinforcement learning, we assume that we don't know what this function is, right? Which is a really good assumption because we don't know exactly how this is actually going to work, how this is going to work. So here we have this vehicle, and then this is like what it can happen. So these are samples. So different samples from different runs. So that's what we get. And then when we sample this, the reason why it gets like more spread out is because I can start in any of these other points here to go to these other points. As you can see, as you keep going to the future, like these clouds, they're going to grow and grow and grow, and they are going to overlap with each other. And this happens, right? And that's why, like, there are lots of approaches that you try to predict in the future, but you give like more weight to the immediate reward, right? Or the immediate behavior, because that's more controlled. We are going to go back to this, but this is the representation of the environment. Okay. Then we have a reward function. So that's the question that you asked before. Here, this reward function, I select that. And once I select this reward function, it is fixed. Okay. So what is this telling me? I have a leader, and I want this leader to be in this area here, in the center. Okay. The followers can be in this donut-like area around the leader. It does not mean that the followers need to be like equally spaced or anything like that, but they need to follow the leader around this. Why is that? Because for my problem, for the problem of like looking at our target, this is the optimal uh, distance for me to get different perspectives. If the follower is too close to the leader, we get like representations that are very close to each other, and then we cannot reconstruct the element really well. If we have followers that are too far, now we have a problem because we're going to have some dispersion as well. So this is like the area where I want these vehicles to be. Okay. If I plot this, I get this. Like if I plot this function here, okay, and again, I don't want to discuss this function because it's not interesting for what we're going to do here. It's this donut, but I designed this. This was our design. We designed that. That's what we want to do. We are calling this cost. Therefore, we want to minimize the cost. So basically, we want to stay in this area here that is this dark blue. As we keep going up, right, to the green, to the yellow, to the red. So that's less preferable states, okay? Like in terms of the reward that we are going to get. Now, observe that sometimes we want the flexibility to get out of like this donut here, like to go around here, because we want to keep in the donut most of the time. Depending on the dynamics of the environment, we have to go out of this donut here. Okay. So when I show you the simulations, so you see what I mean by this. So we defined the states, the actions, we look at what the environment looks like, and we define the reward. So our work as reinforcement learning designers is almost done. The next thing that we need to do is to understand what is the learning objective. In our learning objective, in this case, since we are talking about like cost, we have a cost that is going to be the expected value of the summation of my reward function given the state from now to infinity. Okay, so that's what we want to do. Observe that I don't want to optimize just for one time step. I want to optimize for all the time steps. Okay, so that's why we have this infinity here. So that's what this infinity means. Then we have, but this problem here, we cannot solve. Why? One, we cannot observe all the way to infinity. Okay, that's impossible. We cannot do that. Two, if we have to do the summation every single time step, That's extremely inefficient. Like even if you have like 1,000 points, if you always have to add all these 1,000 points, that's very inefficient. What we do, we represent this problem in an iterative way. And this is like this form here. So throughout this course, we are going to see how we get this form here. Okay. So now what we do, we transform this into the cost that we observe now, plus a prediction of what is going to be in the future. Okay. So this equation here, this way of transforming this equation from a summation that goes to infinity to a summation that is just over one step. So this is the Bellman equation. Is how we transform this. Again, we are going to see this in detail later on. And the objective is to find what are the actions, in this case here R for rho, that are going to create the minimum value for us. So observe that we are talking about cost, and this is minimum. In general, we talk about reward, and this is a maximum, is a maximization. And one problem is the dual of the other. So if we solve something like for a minimization, you can solve for a maximization as well. But this is just a detail here. Depending on the area that you're working on, if it is control, it is very common that you're going to talk about cost. If you're talking about like more general problems in reinforcement learning, you're going to talk about reward. So most of the time we are going to talk about rewards, not about cost. But this is just for you to understand that we can do both. Okay. And the type of equation that we're going to solve is this equation here. Okay. So this is the like all the equations that we're going to follow in this course is going to follow this pattern. What is this pattern? We are going to create a new estimate that is going to be based on the current estimate plus a learning rate or step size multiplied by the target. In this case here, this is going to be the target because this is what is called a temporal difference type of approach, minus the current estimate. That is this value here. Okay. This equation here, if we implement it properly, if you select parameters properly, like for example, here we have this alpha parameter, and we also have this gamma parameter that we are going to discuss throughout this course. If you design this properly, you will have a system that is going to converge. So that's the whole idea here. And we are going to create like a variations of this equation for different scenarios, okay? But the equation is always going to be the same. If you just need to, memorize something, it is going to be this format. New estimate equals the current estimate plus a step size multiplied by the target minus the current estimate. How we do the current estimate is going to vary. How we do the target is going to vary. How we are going to select the learning rate is going to vary. But the format is always the same. The template is always the same, okay? And then we can do this in a system. In our case, we did this, like the environment was a simulated environment, but you can also do this in a real environment, okay? So that's the idea here. And what we do, we plug this into a system that we developed, and then we can actually learn with this. This algorithm, we called it Q flocking because it's a type of flocking using Q learning. What is the difference here from what is done in the literature? Like people solve this with a technique that is called dynamic programming. And in this course, I'm going to explain to you what dynamic programming is. Not because I want you to become a specialist in dynamic programming, but you need to understand where we're coming from. Okay? In dynamic programming, you do need to know what is the model of your environment. So it's a model-based approach. Okay? And a model-based approach, you might think that is really good if you know the model of the environment. So then you can do this. But we are going to see throughout this course that it might not be what you actually want to do. That's why, like nowadays, we are using like these data-based ways of solving problems. Reinforcement learning is a model-free type of system that does not require that we know what the model is, but it is going to be data-based. Okay. And with this, we can actually solve way more problems and in way better ways than if we know everything about the environment. But we follow the same idea. So that's why we are going to start with dynamic programming. In the end, like in this paper, we actually demonstrated that solving this with the reinforcement learning is more efficient than solving this with other techniques like dynamic programming, which at the time was um, um, the state of the art, right? So it's not anymore, but at the time it was actually the state of the art. So here is the simulation. So what do we want to see here? So what do we want to see here? Just we have this leader. The leader is going to fly, and it is following a target on the ground. So the followers are not following the target in the sense that they don't have a tracking algorithm. Okay. The only thing that they want to do is to be around the leader in that donut shape type of thing. Okay. So that's the only thing that the leader, that followers want to do. Then what we want to see here is that the cost, we want to see it going down. Okay. And here from 40 to 60 is that donut that I showed you. So it's from 40 to 60 meters. That's where my desired distance are. So most of the time, I want to see the vehicle within these bounds here. As I mentioned before, these are what we call soft bounds. So sometimes we are going to go out of it, but we want to minimize the amount of time that we go out of it, right? So, but we need that flexibility, because if this was like a hard bounds, so then our behavior would be extremely conservative. Each agent is going to learn separately. So you're going to see that they are going to start with a policy that is very inefficient, but we want it to be more efficient. Okay. So what I mean that they are going to be inefficient. So they are not going to be in the bounds 40 to 60, and the cost is going to go up. Okay. As time goes by, we want the opposite. We want them to be most of the time here, and the cost we want to go down. The cost will not go all the way to zero. Why not? Because there is uncertainty in the environment. So the cost does not go to zero, but it does go down. Okay. Here you're going to see the number of episodes. So we start at the first episode, then we're going to see more episodes, and you're going to see that even with like a relatively few episodes, we can actually learn this in a very efficient way. Okay. Just okay. So I'm going to play this, and so the first approach is very inefficient. They just keep going on circles. Then it's a little bit better, 5 episodes. 10 episodes is a little bit better. Note that one agent is learning faster because it's excited more than the other. So in 20 episodes, they already do like a kind of like a decent job. But with 30 episodes, look at the cost. The cost goes down, sometimes goes up, but it stays in a lower area, and the agents stay within the prescribed area or desired area. Way more than before. And again, it is unavoidable that they are going to actually go out. Why? Because you don't know what the leader is going to do. So what do? In the future, you don't know what the leader is going to do, but you have to react to what the leader is doing. Okay? Yes, there's a question.
Yes, Doctor. Please, regarding the database and model-based, moving from model-based dynamic programming to data-driven approach makes sense, but for real physical system like queue forking, how we handle the safety risk during the try and error exploration phase uh,
Um,
before the
well,
equation actually covers.
so like one thing is that like if you use an optimization-based approach like this, even if we do this, we don't necessarily guarantee that the system is going to be safe all the time for lots of reasons, right? So if you have a model for the system, this model is a nominal model. So in this case, like if we have a model for the system, and this is the issue here, we know more or less what are the bounds of the the distribution, but we cannot predict what the distribution is actually going to do, and specifically the compounding of the distribution. So if you use like a system that is going to be either going to infinity, like a dynamic programming type of approach, or going to a finite horizon, like a model predictive controller of some sort, you will not be able to technically guarantee what the system is going that the system is going to be safe all the time. It is extremely hard to do that. And that then becomes like a very mathematical type of thing. And then no one does that because you understand that that's going to be very, very inefficient, very, very fast. Okay, so in this paper, we actually compare to the solutions, and then we show that the system is going to be not guaranteed to be safe. That's one point.
So even
Um,
we use the large language model, the most intelligent large language model to do this mathematics.
I didn't understand what you're saying. So what do you mean by a large language model in this context here?
I mean, we can use in the agent a smart component like GPT 5.4 to make it
To do
more smart with the
like
system
to make
to
what more
avoid
smart?
to avoid all of this, the error,
So what you're saying is that you can use a large language model that is going to
to
be
handle
able
the
to.
safety risk during try and error exploration for equation actually coverage.
Oh, that okay. So again, I'm not quite sure if I understand your question because so the large language model, you're talking about like giving the large language model an equation,
Right.
and you have the equation, but and then how do you define the stochasticity of the for that for the large language model?
Oh, so we
Because
can't
the
predict.
problem, yeah, go ahead, sorry.
So we can't predict it using large language model. So stochastic, it's more stochastic, so we don't know what happened, right?
Basically, no, you cannot do that. How can you do that? Like you have a bound for what the noise is going to be, right?
Yeah,
Then
right.
in this particular problem, what you need to do, you need to actually have uh, um, um, a system that is going to um, evolve like in the future with certain dynamics. The way that this is actually done mathematically, you have like sets, and then you have the sets that are going to have like this noise that is going to be dependent on the state and the inputs that you have.
Yeah.
With a large language model, I'm not 100% sure how you can actually do that. How are you going to be able to get this system evolving over time with that? You do need to have a model that's what I was saying. It's a nominal model, right? That you say that the model is going to actually go in this way. Then, if you're doing this in the optimal control way, you are going to define what the bounds of the noise are going to be. And then once you define the bounds of the noise, what they're going to be, so then you get like whatever is the system that is going to give you what the best result is going to be. However, you
Okay.
don't know what is the optimal in this particular case because you cannot represent this equation in terms of like the optimal control directly. And then I'm not 100% sure if I understand how you like what you are suggesting to use here instead of using an optimization in this way, right? I do understand that a large language model can actually give you a certain amount of optimization if you define the optimization problem in a way that can be bounded and can be constrained by what the system is. Um, yeah, I'm not 100% sure if I understand your proposal here.
Okay, doctor, thank you.
Okay. Yeah, so sorry about that, but yeah. So in this case here, what we are trying to do is to create a system that is going to learn from the sampling of the data. It's not based on the model because we understand that the model, whatever model you give to the system, it is going to be imperfect. And if you come up with a solution that is not going to be based on the sampling of the system, but is going to be based on the model, that solution is going to be inherently more conservative. But again,
Okay,
yeah, so like throughout the course, we can go back to this, but it's yeah, I need to understand a little bit better what you're implying here. Okay.
okay.
Okay. Any other questions? No? Okay, so we are going to do like a very short break. Maybe like now it's 10:30 here, so maybe to 10:35 or so, just so you can use the washroom or have some water. Just because that's another thing. We need to finish by 11:45. That's because the course was supposed to be from 8 to 11. Now we move to from 9 to 12. But I do have another commitment that it starts at 12. So we need to finish a little bit early. Okay. The second portion of the lecture today is going to be shorter than this one. We are going to be able to finish by then, but it's our break is going to be 5 to 6 minutes. Okay. So I will just turn off my camera. Just a second. And then we'll meet again at 10:35. Oh, sorry. Okay. So is everyone ready to start again?
Yes,
Okay.
Dr. we are here.
Okay. Okay, so we are going to start, as I mentioned, so this is going to be a little bit um, shorter than the previous one. The previous one was just to cover what the problem actually is and to introduce the concepts. And now we're going to talk about like a reinforcement learning specifically, and then how we solve these types of problems with reinforcement learning. Okay. Okay. So this is like in the textbook, this is the definition of what reinforcement learning is. Okay. So it says here that reinforcement learning is learning what to do. So here, what you do is the actions. So what are the actions that we need to execute? Mathematically, this is a map. So it's like how to map situations. And by situations, we mean states, right? So these are going to be the states. Two actions, and these are the actions that we have available, okay? And again, actions are going to be constrained by the environment that we are executing this on. The map, therefore, we usually represent that as pi. That's a policy, and it's going to be a map or a function, and it's going to go from the states to the actions. So basically, if we are in a state, we execute an action. This map is not necessarily a deterministic map, meaning if we are in a state, it is possible that we are going to select different actions. No, because there are some problems that require that the actions are not going to be deterministic. In other cases, the actions are going to be deterministic, meaning every time we are in that state, we are going to choose a specific action. Let me try to give you an example, like a hopefully very simple. Let's assume that we are playing a game like chess. There are certain situations in chess that you are in a position that you should always select one action that is going to be more efficient than others. For example, let's assume that you are close to a checkmate. There are actions in certain situations that are the ones that you should always execute. In other situations, for example, in an opening, and if you are playing white, you need to open the match. There is not one necessary opening that is always better than other ones. Okay. So then you have a flexibility, and then these actions, like whatever is the opening they're going to play, may be stochastic. So that's the idea here. Okay. So this policy can be probabilistic, stochastic, or deterministic. Um, the examples that I'm going to show you throughout this course are of the sort that the actions are going to be deterministic. I'm going to show you some examples where the actions are probabilistic, but you can have one or the other, and it depends on the problem that you're going to deal with. Okay, so just keep that in mind. The idea then is that you're going to learn what to do. And this is extremely important. It's what, it is not how. Okay. So here is how to map, but it's this what to do is not how, it's what. Why? Because we don't necessarily know what we should actually be doing, because this is going to be related to a different quantity. If we knew exactly how to solve a problem, this is not a reinforcement learning problem. Okay. So this is, you can use this, you can use other types of machine learning for that. Don't try to force a problem, like for example, a classification problem. A classification problem is not a reinforcement learning problem. Okay. Can you solve that with reinforcement learning? Yes, you can, but it's going to be way more convoluted and it is going to be way less efficient than if you use a different type of model. Okay. So just keep that in mind. So it's you say what you can do and then not necessarily how you can do it. For example, large language models, they are used for different scenarios. And then the one thing that large language models have been tried, people have tried to use large language models for is to play like complex games like chess or Go. And large language models are not very good at doing that. While other systems, like based on reinforcement learning, like AlphaZero, they are very, very good at that. Why? It's because you're reacting to sampling of the environment as you keep going. And that's actually something that is different, okay? In any case, it is something that you need always to ask yourself, is this problem already, like there is a mapping that is known that I should just be following this. If this is the case, so then you use a different type of learning. If it is something that that no one knows exactly how to solve it, or how to sample it, or if it requires constant interactions with the environment, that's a reinforcement learning type of problem. Okay. Then what we try to do is to maximize a numerical reward signal. So this we call a reward. Usually we represent by R. Okay. Note here the word A because it's one number. So this is usually a scalar. So this is going to belong to the real numbers. Okay. And it's going to be R1. There are versions of reinforcement learning that can operate like in more than one, right? So like 2, 3 values, and this is going to be like um, a multi-criteria or type of optimization, but it's the most common way and the most straightforward way and the most powerful way is when we actually represent everything as just a number that is going to be our reward. Okay. The learner or the process that we are going to, the agent that we're going to develop is not told which actions to take. So we don't, and this is because we don't know what the actions are to take. If we knew, so therefore, this is not a reinforcement learning problem, okay? But instead, the learner must discover which actions yield the most reward by trying them, okay? So this is an interactive type of system. And what is implicit here is that as the learner gets better, the type of rewards and type of experience that the learner is going to get is also better. Okay. So this is something that you have to keep in mind. So this is how reinforcement learning can be done, and then how reinforcement learning differs from other types of learning. Okay. Therefore, there are classes of problems where reinforcement learning is really good for, right? And there are classes of problems where reinforcement learning should not be used. Okay. As I mentioned, if you have a classification problem, you can use reinforcement learning, but it's not the best one. Okay. So what are the types of problems that we can actually use reinforcement learning? Anything that you need to interact with an environment, like in a sequential way, is for reinforcement learning. For example, if you want to play a game, right? So like for chess, Go, a video game, doesn't matter. Reinforcement learning is by far the most appropriate way for you to do it. Okay. It's just because you do need to change the way that you're going to interact with the environment, and then you're going to get information from the environment, and then you don't need to have a model for the environment. That's one way. The other way, the other class of problems is like robots. If you have physical or virtual robots, and here I'm using robots in a very loose sense. Physical robots can be like self-driving vehicles, drones, robot manipulators, robots that walk, right? So like a humanoid robots and so on and so forth. So those are physical, that they do have readings from the environment. Like, they have sensors that sense like force, acceleration, cameras that can perceive the environment and measure things into the environment. Like you can have like a LiDAR that measures like surfaces. You can have accelerometers that are going to measure how the robot is moving. And this encompasses also the vehicles, right? So like I'm using here robots, physical robots, not just as humanoids or manipulators, but also vehicles, okay? But we also have like lots of like virtual robots. So where like reinforcement learning has been used quite a lot. Cybersecurity. So let's assume that you want to have a system and you want to defend your system. And then you want to be able to try to look into the system and then see what are the different approaches that invaders are trying to use to invade your system. So that's a virtual robot that it keeps monitoring what is happening and changes the policies of your system. So it has been used for that. It has been used quite a bit, like for finance, like for example, to make um, um, uh, recommendations for financial markets, like to buy things, to sell things, to invest money in given places. So that's another thing that like a virtual that reinforcement learning has been used for. So I'm using that as a robot. Nowadays, you would call that like an agent, right? So that gets information and then gives you a decision. And these information and decisions, they are sequential, right? So you get to have measurements and then you get to give like outputs. So these systems are, and you have to observe how the system is changing. So therefore, reinforcement learning is really good for you for that. Other things that people have been using this, like for example, for distillation of LLMs, like a DeepSeek. So if you are familiar with DeepSeek, or if you read their papers, so they use reinforcement learning to make your LLM better for um, a given environment. So that's another thing that you can actually use reinforcement learning for. It's really used like a virtual agents as well in communications. So you do have like a communications agent that is going to read like the inputs of a network and is going to make decisions on what are the grants that are given like to um, different devices, right? So like in IoT applications and things and other things similar to that. Okay. So and again, there are like some examples here of like games like Atari games. It's just because they are simpler to see. If later on you can actually take a look at that, but there are other things that you can actually use this for. So the components that we saw here that I want to talk about now, just so we can have a better understanding of what this is the environment, the agent, the actions, the states, the rewards, and the policy. The policy lives in the agent and is going to link the state and the action. And then we're going to see like what each one of these components are. So today we're not going to look at like how they are developed, like for example, specifically the policy. We're going to start doing this next class. But today I just want you to have like a general idea of what we are talking about. Let's start with the environment. So the environment is defined as something that exists like outside of the agent. It's how the agent is going to interact with its world. So the world of the agent is the environment. The environment is going to be changed by the agent. So if the agent does something, the environment is going to change. The environment can change in a big way or in a small way, but regardless, it always changes. For example, let's assume that we are talking about a vehicle. So when the vehicle moves, the environment changes because there was a space that was not occupied that now is occupied. Okay, so that's like a definition of this motion and then how the environment changes. So that's one example that it changes kind of like in a big way, right? Because that particular environment cannot be occupied anymore. Agents that are, for example, finance agents, right? That are doing like investments, depending on the amount that you are investing. So if you're a small time investor, like most of us, so whatever you invest changes the environment because now you have like money that you put in some things or you buy in a stock, right? That someone else cannot buy it anymore. But since there are so many different variables, your action, the action of this agent, is not going to change the environment substantially. Okay. Other agents are going to interact, and then that's going to be changed by the the joint action of all the agents. So, but regardless of that, the environment changed. Okay, so you execute an action and you change the environment. The other thing that this implies is that there may be other agents in the environment that are going to change this environment. And then you have to observe what this change is going to be. Okay. When you observe this environment, you represent the environment. This representation is the state. So the state is necessarily a representation of the environment, and it is most of the time a simplification of what the environment actually is. For example, if you look at the sensors, like in whatever area you are simplifying what the environment is, and then by that simplification, you are going to act upon. And we are going to see throughout this course that there are lots of ways that you can do this. And this should be familiar to you. For example, I'm assuming that most of you are either in engineering or computer science, but maybe some of you are like more of the hard sciences, like physics and so on and so forth. And then all of you have used like models that simplify what the environment actually is so that you can solve for certain things. So if you are an engineer and you represent, like, for example, a car, you probably, like very few of you, have identified the car in all its components. Like, for example, did not develop like a model for the tires of the car. Some of you may have done that, like using like a Pacheco model or something like that, like to see the slippage and so on and so forth. But most of you, if you took a course and you had a car, you represent like the motion of the car just based on friction coefficients that are an approximation of what the friction is. Okay. So that's a very simple thing, but it's very powerful as well. Same thing, like if you were like in high school and then you were looking at like, motion of planets, and then you had to calculate what was the motion of a planet or a satellite around Earth. Most of us, what we do, we represent like Earth as a point with a lot of mass. It's just a point. Like very few of us have ever represent Earth as like a density model that changes in different locations of the surface, which you need to do if you're actually going to do other stuff, right? Because there will be areas on Earth that are going to be denser than other areas, and therefore, like a gravity is going to be a little bit different. It needs to be taken into consideration if we go into these more sophisticated models. But what I'm trying to say is that the choice of the state is going to be linked to the level of abstraction that you want. Okay, so that's something that we need to be very careful. This state is not the environment. This state is a representation of the environment. In reinforcement learning, like when you see something, like observe the state of the environment, you technically have an observation. And then from the observation, you have the state. So meaning that from the observation, sometimes it's O, you get what the state is going to be. Okay. But it depends on the level of abstraction you want to have. So it's going to become clear as we keep going. The other thing is that the environment is going to generate rewards. This does not mean that the rewards are given by the environment. It's an interpretation that you make of the environment. Therefore, it's based on your own capabilities. There are very few situations that you actually receive rewards that are external to you, right? It's always something that you actually generate based on what you want to observe. Like, let's go back to the example of chess. If you have two players that are at the same level, you might evaluate the same position in two different ways. Okay, why? Because you have like a different understanding of what the environment is. If you are at different levels, like different elo levels, that's clear, right? So if you're a grandmaster, you look at the board in one way. If you are like a beginner, you're going to look at the board in a completely different way. So this means that the way that you're going to generate rewards is going to be different. Therefore, this is linked to the knowledge that you add to the agent. And we are going to get to this very, very soon. But the way that the reward is going to be done, it is something that we as designers need to work on, right? It is not something that is most of the time given with a problem. Unless the problem is very constrained, we are going to see some of these in this class, but in the general case, if you're doing research, this is not the case. Okay, so it's way more complicated than this. So that this brings us to the reward. Oh yes, there's a question.
Yes, doctor. So we can change automatically reward function regarding the changing of the environment for the agent. So if the agent working in environment A and moving to environment B, we can automatically change reward function, right?
You could, but in that case, usually you have like two different agents. It's way more efficient to do than if you want to have like one agent that is going to be changing reward functions, for lots of reasons. But the most common reason for this is that you will have to think in terms of like you specialize it's not the same thing, but it's like similar. We specialize an LLM for a medical application, and then you move to a law application, right? And then you just start learning from scratch again. That's going to take a long time, like for the distillation, and it's not going to use any of the previous information that you had. In general, what you want is that your agent is going to be able to deal with like all these different scenarios, and therefore the reward function should be the same. So
So
if you train, yeah,
we can't make multi-model agent or like
yeah, you
multi-model
could do
agent.
that. You could do that, but most of the time, you actually want a single agent that can deal with different situations with the same reward. So then you actually define the reward that is going to work the same way for all the scenarios. If you're doing this like for a self-driving car, for example, you don't want to have like a system that can deal with only the situation when it's dry. There's no rain. Okay.
So
Uh,
we can make a lot of agent and make master agent or to orchestrate
No,
between.
that's what I'm trying to say. You can do that, but that's not the way that people do it. Because if you do it, you have another problem. The problem is that you need to identify when to switch from one agent to the other, and that's not easy. So it's the same thing. Let's say that you're trying to create an agent to fly a quadcopter, and there are solutions that are better than, for example, let's say that one motor fails, and then you can switch to a controller for three uh, rotors. But then you have to identify that the failure actually happened. And that's actually not easy. That's actually
Yeah.
tricky to do. Therefore,
Not easy for computational power or for what?
it's not easy because it's like for the readings, right? It's very tricky to actually um, identify that there is a failure and what is the level of failure. Because the failure can be a catastrophic failure in the sense that the motor just stopped working. And that's pretty easy, right? Because now you have no current coming back. But usually the failures, they don't go this way. So the failure may be that the propeller cracked, right? Or it can be that you are reading the same current, but the torque actually changed. That's not easy to do. If you actually had to switch agents in that case, and that's another issue because now your system becomes what is called a hybrid system, that you change from one to the other, and that switch is going to be discontinuous. So most of the time, you have one agent that is going to be able to deal with all of these situations. You don't want to have specialized agents for different situations. Okay,
Okay,
because otherwise you're going to have to deal with this instability in the system. Okay.
okay, fine. Well,
Okay. So for the rewards, so the reward, as I mentioned before, is received from the environment. We usually design these rewards to create incentives for the agent for a behavior. And as I told you before, that's actually tricky to do, extremely tricky to do. And you don't want to create an incentive to solve in a given way. For example, after AlphaZero, there are things that agents do that is very different from what humans actually do. So there are lots of games in AlphaZero that don't follow the pattern that you learn when you learn how to play chess. So for example, you don't like it in general, what you do, you develop your pieces, you control the center, you avoid motions from your opponent, and then you create a certain attack, right? So if your opponent attacks on a side, right, on the board, the border of the board, you attack at the center. There are lots of games from AlphaZero that they don't follow this. They actually do something that's completely different. But if we had created incentives to control the center, these other games would never happen, right? And now we know that these games, they are, you know, at least more powerful than other games, okay? So you have to be very careful how you create these incentives. I'm going to show you that's like a few types of reward functions throughout this course, but there are a lot. And then this is something that at least that you're going to be able to go to the literature and take a look at what the reward functions are. There are lots of functions that you can use, and they are used for different reasons. And again, this course is not like to cover all of them or most of them even, but for you to be able to understand that there are multiple functions and you can use these multiple functions in different ways. Okay. The next component is the policy. Here, the policy is that pi that I was saying before, that you go from a state to an action. Okay. So here can be represented as this, as a function here. So you get a state, and then from that state, you get the action. So this state representation may be deterministic or not. So you may be 100% sure that you are in a state, or it may be just a probability, so kind of like a belief function. The policy itself can be deterministic or stochastic as well. So the policy can actually map states to actions. And this means that if you are in a state, you always choose the same action, or it can be different. Okay. The objective of reinforcement learning is to find this policy. So that's the objective. That's what you want at the end of this whole thing, is that you want to get like this policy that can solve your problem. And this policy, you can get like a very complex policy, like in terms of like a representation, right? So like a neural network that is going to have like a lots of different layers, lots of different architectures, or you want something that is very simple. Why? Because in real life, you want to be able to read the environment and execute something very, very fast. So if you're doing this, for example, let's assume that you're doing this for a drone, right? A drone needs to be executed, like receive commands 100 times a second. That's what you need to do. So your policy needs to spit out something 100 times a second. If you use a very large model, like for example, a large language model of some sort, that's not going to happen, right? You cannot, on a drone that is going to have everything on board of it, right? So it's not going to be executing things off board. It's going to be everything on board. You cannot have like a very sophisticated system there that is going to be guaranteed to execute 100 times a second. Okay, so that limits what you can actually do. There are lots of different ways that you can do it. So you can start with a very sophisticated, very big system, same way that people do nowadays with LLMs, and then you get like a smaller systems. But again, you need to be able to execute this with whatever physical constraints you have. Just keep that in mind. But the objective in the end is to find this policy. Most of this course, we are going to look at policies because what I want you to learn here is the problem, why we do this way. It is not necessarily like to expose you to a specific um, architecture, okay? So it's just for you to understand the problem from the conceptual side. The way you're going to implement it is going to be different, and then that's what I want you to explore with your project, okay? But the basics, they carry over from the toy problems that we're going to deal with in the course to the more sophisticated problems that you are going to work on in your daily lives later, okay? Another component is going to be the training. That's the algorithm that we're going to use. And there are a few different algorithms that we're going to cover in this class. The way that we want to do this and what the objective is to find the optimal parameters for the policy. So again, the policy is going to be that function pi. So we want to find whatever is the optimal parameters there. Most of the time nowadays, this is linked to a neural network. We try to optimize the rewards. Most of the time, we maximize the rewards. If we are minimizing, we usually call this cost, okay? But again, it's the same idea. So if you maximize rewards, you can think of like minimizing costs as a dual of that problem. All of this is based on interaction with the environment. And this is key as well, because once you get a better policy, the way that the environment is going to reply is going to be different, right? Because you're doing it better. Just think of that as if you are playing, like, I don't know, this is an agent like to play a game of some sort. It can be like a video game. If you start with a video game and you're really bad at the video game, you cannot go past like the first phase, right? But as you keep getting better, you get more and more and more information. But this information that you get is going to be more and more sophisticated or harder for you to actually deal with. So you need to deal with that as well. So interaction with the environment is key. Therefore, reinforcement learning is used in what is called sequential problems. So you go from time 0, time 1, time 2, time 3, time 4, and then you get all this sequence of actions. It is not an isolated action, but it is a sequence of actions that you need uh, to define. Okay? So when we are formulating a problem, we do need to know how this problem is going to be defined. And there are different ways for us to define the same problem. And again, some of you are engineers, some of you are computer scientists. Computer scientists and engineers represent problems in same problem in very different ways. Okay? Very, very different. So for example, computer scientists usually represent things into this Bayesian reasoning type of things, which is one way of doing a Kalman filter, right? But computer scientists usually don't know anything about Kalman filters, and engineers usually don't know the way that computer scientists solve for Bayesian formulations, okay? So there are different ways to formulate a problem. That's what I'm trying to say. And then there are different ways that you can actually represent this in reinforcement learning as well. There are different ways that we can represent an environment. I'm going to talk about this very, very soon. And this is important. You have to decide which one is going to be better for the architecture that you're going to be using. You have to define what the states are. Like this, defining what the state space is, in terms of what you can actually do, like state one, state two, so on and so forth, right? So this is something that you that you need to do. Okay, it's very important. What are the observations? So what you can see from the environment, and what are the actions? The actions are usually the easiest things because this is going to be linked to the definition of the problem itself. If it is a physical system, there are physical limitations to what you're doing, right? If it is a car, and then you decide that you want your car to move sideways, this is not going to happen because your car is not equipped to do that unless you're going to change. There are these cars that you can turn like all the four wheels, but this is not necessarily the case in most of the systems. How are you going to represent your problem? How are you going to do your policy? It's going to be a table. It is going to be a neural network. If it is going to be a neural network, what type of neural network? Are you going to approximate the values? Are you going to approximate the policies? What are you going to do? So this is something that we are going to cover during this course. Is the representation discrete or continuous? Okay. As I showed you for the swarming problem, so that particular formulation is discrete, but the problem is actually continuous. So why did we do this? Why we didn't do this in a continuous way, and so on and so forth, right? So this is a decision or something that has to be clear in your head. And sometimes there is no right or wrong answer. More convenient for you in that particular situation. So, and finally, what happens if you face something that you have never seen before? Not do anything? Are you going to do something? It is better to freeze. It is better to just do something that it may not be the best thing to do. You need to define this, and you need to understand the limitation of what you are doing. So all of these we are going to follow and do. Very simple, like tic-tac-toe. Everyone here probably played tic-tac-toe at one point in your lives, right? And here it is like we are doing like an agent, and then the agent, let's assume that it's like this circle one, but it could be the other one, it doesn't matter. And then we need to define all of these different things. First of all, we need to define these states. And there are different ways for us to represent states. So one way to represent states is to represent this as an image. And this is totally possible, right? So you can actually get the board and represent as an image. But computationally speaking, it might be not the best way to do it. Why not? Because there are only 9 spots here, and we can represent these 9 spots as a matrix, which is way more concise than an image, right? Because the image would be like the pixels. So it could be a matrix. It could be representing this as a vector with 9 positions, right? Depending on the architecture that you're going to be using, it is better to use a vector than an array as an input. A vector than a matrix as an input. So you have to define what that is. Regardless of this, in the end, we only have 9 spots here. Therefore, if we assume that each spot can have like 3 possible values, it can be a circle, it can be an X, or it can be empty. You have 3 points, 3 values, 9 positions. The maximum number of states that we can represent is 3 to the power of 9, which is not no, there are less states than this, right? Because, for example, the state with all circles, like all position circles, this does not exist. It is an impossible state. Regardless, the maximum number is 3 to the power of 9. This means that this is a very simple problem to solve, right? Because you can represent this as a tree, and you can solve for what is the solutions. And this has been known, right? So what is the best strategy that we're going to follow when playing this game? In the same way, so this is for the states. So we can represent as a matrix, we can represent as an array, 9 numbers and 3 possibilities. And this is going to be the maximum number of states that we have. The actions are also simple, right? So you can define actions as putting a mark in each one of these positions here. Now, you can go like a fancier and say, okay, so if I'm in this state here, I cannot put an X on top of the circle. Therefore, I don't have 9 actions. I actually only have 8 actions. You can do this way, but this is usually not the way that we do it. And the reason we don't do this way is because if we do it, we need to create a system that is going to contextualize what we are going to be representing. For this problem here, this is simple to do. There are other problems that this becomes very complicated. Therefore, we usually allow 9 actions. So this is for the states. The number of states here, I'm just going to put like the norm of the states, just to do this way, is going to be 3 to the power of 9. The norm of actions, like number of actions that we are going to use, is going to be 9. Okay? So, and then what happens if we put like an X on top of a cell that was already occupied? We give the system a really bad reward, and the system is going to learn that that's bad. Okay? Or alternatively, what you can do is that you don't allow that. But recall, like just you have to keep this in mind, that this makes your algorithm way more complex. Okay? And this means that your algorithm is going to take much longer to run because it's going to be more complex. Then we need to define the rewards. One thing that we can do is that, well, if you do an illegal move, you get a really bad reward. But let's assume that you only do legal moves. So what are the rewards that we can actually have? In this case, we only have 3 outputs for this game, right? So the rewards, we can actually say that if we lose, we get a negative number. Let's assume -1. If we tie, we have a 0. If we win, we have a 1. Okay? It can be that simple. And then the agent is actually going to play that way. Now, if you want, it depends on how you want to do in this game here. But this game is a very simple game, and it only has these 3 outputs. But we humans, it is different for us, right? Because sometimes we have a bigger aversion of losing than pleasure into winning. If you want to do that, you can say that, for example, the reward for you to lose is going to be -10. If I tie, I get a 0. If I won, I give a 1. If you use this reward function as compared to the other reward function, the results are going to be different because now you have like an agent that is going to try to avoid losing. Okay. So you will need to define that, how we are going to do this in the system. And then we need to define what is going to be the format of the policy. So it's going to be, I don't know, like a neural network. It's going to be a table. What is it going to be? Okay. So that's the different ways that we can represent this. And if we have a more complex problem, we need to represent this in this more complex problem. So let's assume that we have this one here. This game here is called guard a territory game, or it's called like a pursuer evader target problem. There are different representations of this. This is the guard. This is the invader. The invader wants to go to the target. The guard tries to avoid the invader into getting to the target. This is a very interesting game because if we define this in this way, and then you say that the rewards are going to be symmetric, like for example, getting to the target here or and avoiding the target. So this is going to be like same value. And the value of the game is going to be the distance to the target. So then the guard, the invader, tries to minimize this distance. The guard tries to maximize this distance. So this is a game that is what is called a zero-sum game, right? So they are going to get like it is symmetric, okay? Then if you do this, you can actually find what is the optimal solution. So there is like a definition of this, mathematically speaking, and this was done like in the 50s. And then here we know that there's this circle that is like what we can achieve. Like this is like the frontier that is the optimal frontier. Like if both of them, they do the optimal solutions. And this point here is going to be the optimal point. This is what is sometimes called the Nash equilibrium of this problem here. But this is predicated that both players, they are going to play the optimal solutions, okay? If they don't, let's assume they have an irrational guard. Like the guard, instead of like going to the point that would be here, right, goes after the invader. What happens is that the invader can get to the target, okay? And this is something that is not going to be necessarily good for the guard. But if you are the invader, so this is actually going to be better for you because since the guard is not doing something that is optimal, you can take advantage of that and get to the target. So that's the whole idea here. You should understand that this problem here is a continuous problem. And on top of being continuous, this problem here is and of like I don't know, because if it is continuous, it is an infinite number of states. So you can represent this. Usually this is represented by the position of the evader, of the guard, the position of the evader, the orientation of the guard, the orientation of the evader. So these are 6 positions. The position of the target. So now we have 8 positions. And then for the evader and the guard, we have also the speeds. So it's usually representing 14 dimensions. So this is a very large dimensional system that you can actually define. You can represent this as an image, as relative positions, and so on and so forth, but it's always large. Then, depending on the approach that you're going to use, you can learn this faster or slower. What I'm going to show you here is something that we have done to make this system to be able to learn in real time with limited information. So we used, instead of a neural network, we used like a fuzzy system to learn this, okay? And then you're going to see how this actually can do. And this is online learning. So the systems are running online, okay? So here, this is the irrational guard. So the guard is going to go after the invader. And this is the first experiment. Since we initialize this with a controller that is based on a fuzzy system, the controller is going to kind of work. But you see that the controller for the invader is not able to get to the target. So here is the invader, here is the guard, and this yellow mat here is the territory, is the target. So you see that the invader gets close to the territory, but it does not get to the territory. Okay? And the guard is going after the invader. So it's a very bad policy for the guard. What happens is that the invader overshoots and gets captured. Then, after like 10 episodes, what the invader actually learns is to cut in front of the guard and go here. And this is similar to what kids do when they play tag, right? So they will just cut in front and go straight. And then it does not get captured. It reaches the here, right? And we can show mathematically that this is close to an optimal policy. If we have a learning invader and an optimal guard that does everything optimal, what the invader does is what you should expect. It goes to a point that is going to be the optimal point, the Nash equilibrium. Okay. And all of this is learned based on data. This is not learned based on models or anything like that. You just have like a rewards, and you have a format of the controller that is such that the number of parameters that need to be tuned is small enough that you can actually learn this in real time, and you can actually put this in vehicles with like a very basic type of controller. Okay, so this is something that is very, very important for what you're going to be doing. So the objective of this course is that by the end of this course, you understand these concepts, you understand that there are different ways to solve these types of problems. There are advantages to solve this problem with a data-based approach. And this data-based approach is going to be superior to model-based approaches. Okay. So that's what we want to see at the end of this course. Okay. So this concludes like the slides for today. Is there any question? No? Okay, so just some housekeeping. I have
Doctor,
already sent, yes.
regarding the project, can we advise us how we can choose the idea for project, or can you help us with some idea for project? Just to,
So you can choose your own project if you wish. Um, we are going to circulate some ideas that you can actually do.
okay,
Um, uh, you are going to do a proposal for your project so that we can actually see if this is doable or not, right? Because you don't have too much time to do the project. We are going to share some ideas, and you can also like propose your own ideas if you wish.
okay,
But keep in mind that it does need to be something that is not too big, it's not too small, right? So that's why we want to give you some feedback.
okay. So you waiting you for the project idea that you will publish
Yeah.
on Q.
Yeah, yeah. So, but it's I mean, we are too early in the course for you to actually think about the project, right? It's just because we didn't cover enough material for you to get. I want you to get like a little bit more exposure to what we are going to be talking about
Okay.
before you can actually look into that. Okay, but yes, but we are going to share that on Q.
Okay.
Okay. Okay. So the other thing that I want to mention is that like our classes are going to be 9 a.m. Uh, here Eastern Standard Time. So I sent you invites for the next 3 lectures, I think. I'm going to change that, and I'm going to put all of them to the same time. Okay. We should have um, some time, like for discussions. Um, the TA is going to have like some office hours that is going to help you specifically with the assignments, and the TA is also like a later in the course is going to have like some lectures that the TA is going to give you tutorials, but the tutorials are going to be given in the lectures. Okay. And the reason is that we've tried to do this separately before in the past, not just in this course, but it's other courses that I teach, like a kind of the same material. And this does not work really well because different people are going to have different commitments, and the time that people actually have, like to be exposed to things, is during class. right? So I want, like, that's why like the TA is going to do this during class, but it's going to be later in the course. So once we do the basics, so the TA is going to do that. And this is going to be a more practical, like a direct type of lecture, right? So tutorial-like type of thing. Okay. But I'm going to use like on cue for letting you know that that's what we're going to be doing. Okay. Any other questions? Okay. No. So I'm